Okay. Well, welcome everybody to the second part of Net Zero Emissions Workshop on the 19th of May, of course, brought to you by the SEG Virtual Workshop and the European Regional Advisory Committee for the SEG. So, as a reminder of the workshop objectives that you saw on the first day, this workshop is focused on net zero emissions for carbon capture and storage, principally in Europe. It's focused on the European experience because Europe has great ambitions for being the first climate neutral continent, using a modern techniques and resource efficient economy. And that's in the context of the European Green Deal, of course, to be neutral by 2050. So CCS, carbon capture and storage, is foreseen happening in two steps. Initial decarbonization of power and industrial emissions. Those are areas, of course, where the carbon dioxide concentrations are highest and easiest to capture the maximum amount. And in a second step, moving to a hydrogen economy, with blue hydrogen requiring CCS whilst green hydrogen is deployed. This direction, this motivation is perhaps best encapsulated with some of the comments by the Minister for Petroleum Energy in Norway, Tina Bru, with the Longship project, aspiring to cut emissions but not halt development. So what do we mean when we say CCS decarbonisation? Firstly, we're looking at decarbonising power generation, capturing the CO2 gas from power stations, gas-driven ones as backup to renewables as they are rolled out, and also to decarbonise industry and some of the more carbon-intensive industries such as concrete manufacture, fertilizer fabrication and steel production. And the hydrogen part initially will be deployed as blue hydrogen, capturing the CO2 that's generated in fabricating that blue hydrogen, while the green hydrogen production is rolled out using renewable energy. So the workshop program, most of you will have seen day one, which was a global overview. Today, we're going to talk more about the details of reservoir characterization, properties and key elements. And day three, we'll get more into monitoring and the regulatory framework, and that occurs on June 9th. Just a quick sneak preview of one of our participants today, NGI, talking about some of the more reservoir scale problems in modelling and research. And we look forward to those presentations from NGI. So this is the program for today, with a short introduction, of course, to begin with. And then we'll be looking at injection of CO2 into depleted gas fields with low reservoir pressure from TNO, the Netherlands Organization for Applied Science Research. Then fault and caprock integrity during injection from Ellen Skirtevit from NGI, which is the Norwegian Geotechnical Institute. Then on into pressure and seal capacity in unconventional CO2 storage units from Peter Bedlam from UNIS CO2 Lab, which was started by the University Center Svalbard. Then there'll be a short break, and then we move on to Joonsang Park's discussion of how electromagnetic data can contribute to subsurface characterization and monitoring, again from NGI. And finally, there'll be an overview of the operation and delineation for potential CO2 storage unit in the high Arctic Norway and Svalbard from Snorre Olhausen, again from UNIS CO2 Lab. And that'll be followed by a discussion and summary, which is perhaps one of the most interesting parts of today. I'd like to give a shout out to the organising committee, many of whom did far more than I did in bringing this workshop to realisation. Most certainly to Emin Sadikov from Equinor, Shiv Dasgupta from the SEG, Gabor Zeli from HMMS, Adriana Ramirez, TGS, and Fiona Sutherland from BP. And lastly, a big thank you to our sponsors who helped make this workshop a reality. And I'd encourage you very much to go to the virtual showcase, which is just next to the registration page on the SEG organization events. And there's plenty of material there if you'd like to find out more about our sponsors. Our next speaker, Joonsang Park from the NGI. He's going to talk to us today about how can electromagnetic data contribute to subsurface characterization and monitoring of CO2 storage in the North Sea. Thank you, Joonsang.
Hi, thank you, Anthony. Do you hear me now? Okay, thanks. Okay, thanks for joining this presentation. My talk is about how we can use EM to contribute to CO2 storage in North Sea. My co-author is Hector and Guillaume Sauvin and Eileen and Lars Grande from NGI. And we are like a geophysicist and rock physics and seismic and geologists to contribute to this talk. Okay. Yeah, so today I will briefly start with brief introduction and motivation, and then what's the CSEM briefly, and then I categorized the three different storage potential in North Sea: shallow and intermediate depth and deep cases. And then at the end, I will discuss about how we can tackle with the infrastructure effect interfering with the EM data, which are also related to borehole to seabed, the EM case. And at the end, even how we can also look at the fault to leakage through EM, through synthetic data study, and then at the end with the concluding remarks. Yes, so normally the EM is not well appreciated or well chosen as a main tool for CO2 storage. And so, but I wonder what we know about the really EM potential in North Sea. And why it's not selected as a main tool. And so what can be done or what should we do to improve this? That's the sort of motivation for this talk. So first, what's EM? Control source electromagnetics. It's quite similar to seismic. So we tow electric dipole, horizontal or vertical source on over the seabed, and then we put the receiver and we tow along the seabed. And then when we don't have any target, then we will not see anything. But when we have a target, then we have a strong reflection to the receiver. So as mentioned, we have two choices in terms of a source, horizontal or vertical electric dipole source. And we normally use operating very low frequency range, since the seabed is quite conductive. And then we can choose quite different options for the receiver. We can choose electric, 3 different directions, or also we can choose magnetic receivers. And our goal is to find the conductivity or resistivity profile in the subsurface using this technique. And then normally we look at the data in terms of AVO or PVO, amplitude, phase versus offset, and also look at the sensitivity. We use quite often normalized AVO as well. So basically, this is one example, synthetic case, but yeah, where you don't have a target, you don't see much difference between the background and with the target. But when you have a strong target, you can see clearly the target from the EM data. So that's the sort of a brief introduction of the CSEM. So as I mentioned earlier, we categorized the North Sea candidate for CO2 into 3 different depths: shallow and medium or intermediate and deep. The first shallow is between, it's a less shallower than 1,000 meter depth. And there are many candidates, Kade or Utsira field, and Utsira is like a Sleipner case. And the intermediate depth is between 1,000 to 2,000 meter depth. And Ellen mentioned earlier about some detail about the Smehaya. That's the typical candidate in North Sea, which is consists of Songnay field formations and also near to Troll field. And the last target is the deep. as known these days, well known as Aurora, which is a Yuan's formation, which is south to the Troll West gas field. And this is the field that in Norway is developing at the moment. So we have a 3 different candidates in North Sea, and then these 3 candidates have a different characteristics in terms of EM, and that's what we are going through today with some examples. First, the shallow is a Sleipner. Luckily, we have EM data from Sleipner, marine EM data. So what you see here in the map is the Sleipner map, and this gray is the CO2 plume map with the seismic in 2008. And then same year, they had the EM survey over this gray CO2 plume area with the receivers on the seabed about 500 meter spacing. And then at the same time, they realized that there are many seabed pipelines crossing this EM tow line. So then you should have a strong interference effect between EM with the seabed pipeline. Nevertheless, we tried to invert using our 2.5D code and with a different inversion strategy. First, we just use the standard 2.5D EM inversion without doing much to the data or inversion algorithm as well. And then we could able to see at least we could see the CO2 plume with higher resistivity anomaly compared to the background. And then what you see in the background of this 2D profile is seismic image. You can see that EM anomaly was showing up a bit higher up than the real seismic image. And then we tried to remove pipeline effect by using filtering, but this time was done as a manual filtering. So we took out the data looks like very contaminated by the pipeline. Then we can see that the anomaly is get closer to the seismic target. And we did some more tuning in our inversion parameter, like inversion grid size, and then also some geometrical effect. And then we were able to be recovering higher anomaly, which is also close to the seismic target. So in the Sleipner case, it's shallow. So we were able to map quite well the CO2 plume in data from 2008. And then with this inversion result, we used the rock physics model for each grid, because from each grid, we have anisotropic resistivity. And then it is well known that the Sleipner case, we have a multi-layer system within the mudstone layers, which gives us a quite strong anisotropic effect in terms of resistivity. So this average effective resistivity can be translated into CO2 and the background resistivity through this effective medium rock physics model by assuming that the fraction of the background and the CO2 is about 10% and 90%. Then we find that the pure CO2 resistivity and also background resistivity, and using this resistivity index, and then we can recover what's the saturation of CO2 in the Ujira case. And then using this simplification, then we can recover the mass of the CO2 in the reservoir. And just going through this from resistivity into resistivity index, and then saturation, and then using this simple formula, then we can recover the mass of the CO2 in 2008, just based on EM data. That was about 10 million tons, which was also close to what they injected according to injection data. So next we move on to a bit deeper candidate, which is Smehaya. And as Eileen presented earlier, the Smehaya is east to the Troll field, and it is bounded by 2 regional faults. To the west is the Beta fault, and it's Oigara fault to the east. And our interesting area is alpha structure here. And we took this the Equinor in the early stage of this Smehaya. They suggested 3 suggested really location 1, 2, and 3, and we took this number 2 as a case study here. So Equinor did in Northern Light project, they did a reservoir simulation for this as this number 2 location, and we took this cross section and which is shown here, the red line. And we made a 2D synthetic EM data based on this. For that, we used the inline component only. And then especially we used a lot of quite many different frequencies up to 5 Hz because as you can see in next slide, there are many thin layers, and also the CO2 plume was quite thin, about 50 meter thick. So what you see at the top is the the true resistivity model that was made based on reservoir simulation that's shown in the previous slide. And this is again 2D modeling exercise. But we used the COMSOL 3D to calculate the synthetic data to invert, and then we used the NGI25EM, another inversion code. And you see the 3 different monitoring years. So to 2020 was the baseline before injection, and then 10 years injection is 2030. And we have a bit stronger resistivity anomaly showing up. And then the last year of injection is 25 years, the 2045. And then you will see the larger and stronger resistivity anomaly here. And then we did the inversion study based on this true model. And then you can see that the baseline was recovered quite well, although we cannot capture all those thin small layers, although we used quite many frequencies, quite high frequencies. But we capture rather well about the main high resistivity background models. So based on this resistivity inverted model, and then we use this as initial model, and we inverted for 10 years injection and 25-year injection. And the result is shown here. You can see that we can see a small higher anomaly showing up in 10 years and also a bit stronger. The main thing we could say here is that the resistivity value could be a bit questionable because you can see that there are big difference, but the size of the plume is quite close to the true model, and also the depth location. The last candidate was a deeper case, which is Aurora. The Aurora is a Yuan's formation, as I mentioned earlier. It is about 2.5 kilometer depth from the seabed. So it's quite deep target. And so there are some uncertainty about the EM signal sensitivity. It's questionable. So here we made a very simple synthetic model. We made a box-shaped reservoir, CO2 plume in the similar depth as the Aurora. And then we deployed the 3D EM survey. And then we did a parametric study, which is ongoing, but I will show you some preliminary research today. So in the parametric study, we changed the CO2 plume size, 5 by 5 and 2.5 and 1.5 square kilometer. And then we also tuned the plume resistivity. And also we also tuned the background resistivity, because that background resistivity contrast between CO2 is also quite important for EM data sensitivity. And then in addition to that, we also parameterized the survey parameters, which are source frequencies, and also we play with the different direction EM receivers, and also different direction EM sources, which is including vertical source and receivers as well, which is also was not very popular in the early stage of EM survey, but these days are very standard and well appreciated. Yes, so this is a bit have the busy slide, but I will not go into any detail. I will just show you the pointing out the main things that you need to learn here. Basically, I'm showing you only the 1/4 of all the receivers that I use, because all the model was symmetric with respect to X and Y axis. So the red are all the receiver point that I used. And then we here, so I like if I go back to one more slide, so I used this type of survey layout, and then I calculated all the responses all three different direction sources and 3 different receivers. And then I calculated so-called value of information, which I define in my study as like the data point, which gives you 20% higher sensitivity compared to your background. And then that in terms of the total data set. So if you have if you have a 10 data set which show you higher than 20% sensitivity, then your value of information is 0.1. So value of information is range is from 0 to 1. And also I took into account the EM signal noise level. So then each receiver, so I have like EZ and JY. That means at this point, the value of information is 0.1. And then the most sensitive receiver source configuration is the EZ receiver and then Y direction source. So as you can see, depending on where you are in your this survey layout, you need a different direction of the receiver and sources. That means it's very important to take into account the multi-component receiver and sources to be able to detect something from like Aurora case. But the picture will be different if you go to intermediate and shallow cases. And so this was 1 ohm-meter background case. And then you can see that some parts is quite, even you don't see anything at all because it's quite deep target. And so if I increase the background resistivity, then since my signal is getting stronger, so you have a higher skin depth, that means the signal can penetrate deeper. So you can see that you get the more sensitivity even the further offset. The receiver is quite far away from this reservoir as well. But of course, since you have a less contrast compared to the CO2 target, the value of information can be smaller, up to 0.17. Yeah, and then one thing interesting feature here is that this is the middle line when you have a 5 kilometer square meter target on the seabed, and these receivers has almost no sensitivity. That means you don't see it at all. So that means you need to 3D survey layout, and then again you need to use the multi-component source and receivers. Yeah, and then as I mentioned earlier, we have on the seabed there are many pipelines like a Sleipner case. So we need to tackle efficiently the interference between the EM data and structure. And the structure is very small in geometry. So if you that include all those detail in your simulation, then you never finish your calculation. So then we try to come up with the efficient technique. So we make an effective anisotropy medium or line EM equation, which can replace the full wave equations, and which works quite well with certain errors. And then we try to quantify the errors at the moment. And the result will be presented EAGE this year. And then this is onshore case, not the marine, but to show you one good example of how borehole to surface seabed EM can be efficient to monitor CO2 injection into the reservoir. So this is a case study in Brazil. It's called Miranga Field. So since this is all the oil field, there are many wells existing. So we can do quite many things here. So for example, this is an injector of CO2, and then we have many monitoring wells. And this pink line is showing the extent of CO2 in each step. So we calculated the response on the surface EM field and compare between different stages. So this is well number 1, 2, 3, 4, and 5, and so on. And these are the different plume size. And then the color shows the difference between 2 different sizes. So this case is difference between when we don't have any CO2 and when we have this plume. And this one is this plume difference with this plume size EM signal. As you can see that as you go to the down, the plume size is getting bigger, and then from the surface EM field, you can see that clearly where the boundary of the plume, which is quite interesting. And but this is a really synthetic data study to just to demonstrate how surface borehole EM can work if we have access to such many wells. Of course, it's not yet realistic in marine because it is quite expensive, but yeah, it's a good demonstration at least. Yeah, I think this will be the last example. Then finally, we want to see how EM can be used for the monitoring or characterization flow through the fault. So as mentioned, Aileen mentioned earlier, there are this beta fault in the Smehaya area, and we believe that it is very sealed fault, so we shouldn't worry about any leakage. But here we just made the assumption that what if something is leaking, and then to demonstrate what we could see with the EM if anything at all is leaking along the beta fault. So we made this 60-degree deep fault in our synthetic model, and then this is the CO2 plume. And this yellow is indicating something is some of the CO2 is flowing through the beta fault. And then we change the leakage rate, and then depending on leakage rate, and then depending on the fault size, you will have a different height, and also function of the saturation. So here is again the very busy plot, but the main thing is that to be able to detect any leakage through the EM, first of all, the amount of leakage has to be rather large. For example, this each line is the leakage rate compared to the how much that we injected. So this is 1% leakage, 2%, and so on. So it has to be rather high rate. Then this green and yellow is sort of a detectable range, and the red is undetectable range with EM. So as you can see that the injection rate rather has to be high. And also this is the CO2 saturation in the fault, which is also we assume. And then this is rather has to be high. And then, but still useful thing to learn here is that in EM, marine EM, so far these days, mostly inline data was used, but lately we also looking at the vertical source and receivers, which shows actually much higher sensitivity compared to inline EM data. So that's something also we need to learn from this exercise. Yeah, and also in the abstract, I mentioned something about the magnetotelluric application for fault monitoring, and it's still ongoing. So, and also I have some issue with what's the noise level to take into account. But at least apart from the noise issue, is magnetotelluric. If you are in the right place, for example, if you are very close to just above the fault, you have a very quite high sensitivity as the control electromagnetic data as well. So that means empty data can be quite a good cheap solution if you are in the right place. Yeah, okay, the conclusion is that yeah, at least based on what we presented here, we can see that the EM data can be useful for both characterizing and monitoring of CO2 storage in North Sea. And then also we discussed in our consortium quite a few times that we had the data from Schleifner from 2008, and now it is to 2021. So I think it's kind of a time that we should think of a second EM survey in Schleifner, so that we can really demonstrate how EM is useful for CO2 storage monitoring. Yeah, thank you for your attention. And this is the project that supported the work that presented here. And we have many partners and funding agencies as well. Yeah, thank you so much.
Mr. Park, thank you very much for your very interesting presentation.
Gas production. We see currently that proponents of CO2 storage in the Netherlands propose to bring depleted fields back to, let's say, 90% of the original pressure. And the idea is that by bringing the reservoir pressure back to hydrostatic or just below perhaps, an additional safeguard against leakage is built into the project. So by keeping the pressure in the depleted field after storage to just under the pressure of the surrounding formations, leakage is made less likely than when you bring it back to the original pressure.
Okay, thank you. Also, there's a question for you. The yearly rates that you mentioned seem high. Most wells only do around one, looks like milliton per year. How confident are you that these high rates you mentioned, 5 millitons per year, are achievable?
Yeah, so the results I presented are, well, if you like, work in progress. So we have yet to combine with, or at least I should say in the results that I showed, not all limitations to injection through the wells have been incorporated. I mentioned flow rate leading to potential vibrations should be taken into account. Bottom hole pressure limits need to be added, both from the point of view of not fracturing the reservoir and from the point of view of not affecting too much, perhaps, existing faults in or near the wells, where low temperature CO2, when it reaches such faults, might destabilize the fault. So the analysis of that is not included in the examples that I showed. So for now, the numbers in my graphs are a bit optimistic. I would agree with that. And they will certainly be lower once we combine with all other reasons to keep the system safe. So we are doing that. I was just not showing the latest results. Thank you for noticing this.
Okay, thank you. One more for you, and then I think you're off the hook for a little while.
Sure.
Were you showing injection of liquefied supercritical CO2 or just pressurized gas?
Yeah, so in my graphs, both were sort of hidden. So the Porthos project, as some of you might know, plans to inject CO2 in gas phase during the early phases of storage, when reservoir pressures are low to very low. Over the course of time, when reservoir pressure increases, the entire system will be switched over to handling CO2 in liquid phase. So over the course of its lifetime, a CO2 injection well will see everything, basically. It will see gas phase initially. It will see two-phase conditions, and then towards the end of its lifetime as an injector, it will see liquid CO2. We are also investigating whether it's possible to start up a system with CO2 in liquid phase, but that's ongoing work. Thank you.
Excellent, thank you. This question is for Joonsang. So the question is, were the 2.5D CSEM inversions Gaussian Newton Occam or a more finite difference conjugate gradient?
Oh, sorry. Can you repeat again the last part of the question?
Sure. So were the 2.5D CSEM inversions Gaussian-Newton Occam or a more finite difference conjugate gradient?
Yeah, it was second. Yeah, close to second, but not exactly the second. Yeah. No.
Okay. So
Yeah, we
close
used
to the
yeah,
finite different conjugate gradient. Okay.
sort of. Yeah.
Okay, great. Thank
Yeah.
you. We have 2 more questions for you.
Yeah.
The second question, might the resistivity anisotropy be greater? If greater, would that help with the depth conformance of the resistivity imaging with the seismic?
Sorry, can you repeat again?
Sure. So the person was curious whether or not the resistivity anisotropy might be greater. I'm not sure greater. And if it is greater, would that help with the depth conformance of the resistivity imaging with the seismic?
Yeah, probably yes. But not the anisotropy doesn't have to be always high when we inject CO2, because I mean that happens especially for Schleifner, because we have this layering system that gave this high resistivity anisotropy, high anisotropy anomaly in Schleifner. But if you have a reservoir is rather homogeneous, then you may not expect that high anisotropy resistivity. I don't know if I answered to the question. If not, then please send me again the message, then I can.
Perhaps sorry, Laurie, sorry, Joonsang. I might jump in there because that was my question. Yeah, I appreciate that the reservoir may not be very anisotropic, and this is for the real data, the 2D line you had, I forget where it was, but yeah, for the real data, not the synthetic models. The overlying shales, I'd assume would be fairly anisotropic, and if you get the anisotropy wrong there, it can affect the depth conformance of the resistivity inversion with respect to what you see in the seismic. Now, I can't remember.
Yeah.
I can't remember what anisotropy you mentioned there when you were working on those data, but it seemed to me to be a bit low, and I was wondering if you'd looked into that further.
Okay. No, actually, I mean, you're referring to Schleifner, right?
Yeah.
Yeah. Yeah, it's yeah, we see high anisotropy also in the overburden, not only the reservoir, but we haven't really concluded what is causing that high anisotropy in the overburden. Yeah.
Yeah, my guess is it might be the shales, and unfortunately, it's kind of tricky to deal with that in only a 2D inversion. 3D would be easier, I guess.
Yeah, I guess also you need a more component to run, not only the inline. If you have a vertical,
exactly, yeah,
you could have been more sensitive. Yeah.
Okay, thank you.
Yeah, thank you too.
All right, we have one more question for you.
Yeah.
And they ask, did you look at this assumed lower coupling of the pipelines with a vertical CSEM system?
Yes, I looked at it, and the order is quite similar to each other. But the one thing about the vertical might be because I could be wrong, but the vertical normally have a shorter offset than inline. So maybe the interference can be a bit easier to control, I guess. Yeah. But the interference, of course, depending on the configuration. But yeah, it could be less than the inline as well.
Thank you. All right. Do we have additional questions from the audience?
I can ask a question. So the Europe Regional Advisory Committee with this workshop has attracted a lot of people with different backgrounds, and we have a lot of students. So there's some students that are looking to find where to contribute with their masters or PhDs. Can each one of you provide some ideas of where you think that there will be much more value for, or in your view, you would recommend students to do more research on? Where are the biggest challenges that are not solved? It's a hard question, but just think a little bit about your student days and what would you recommend the students to do? Who wants to go first?
Yeah, I can go first. Sorry. Can I go first? This is Philip.
Please.
Yep.
Go ahead, Philip.
Thinking about the case of storing CO2 in depleted fields, I think there are still lots of questions that that could benefit from R&D activities. So even though we have CCS projects in that are developing CO2 transport and storage projects using depleted fields, I think there is still enough out there that we do not yet completely understand. And just a few topics are, as far as I'm concerned, are about how in a network that links several such fields, each with their own conditions, each with their own properties, how does that work? How do you make sure that the CO2 goes where it should go? How certain can you be how much CO2 is actually going left and right? Also, I think there is work to do around uncertainties. So we can do a lot of modeling along the lines that I showed, for example, but hidden in those, well, not yet hidden, not yet included in such graphs is the uncertainty we have that arises from limited knowledge of the subsurface geology. So if we are honest and try to propagate that uncertainty into predictions of the behavior of the field as we inject CO2, what do we see? How large is the uncertainty in anything we say about conformance of the operations? So what are the uncertainties in our model predictions, and how does that compare to what we can measure with our monitoring system? So along those lines, I think there is still lots to do.
Yeah, that's a very interesting point. Uncertainties has been a weakness, I think, also if we think about oil and gas, we do measure uncertainties. We are not very good at tracking them from one data set or one silo to the next one. So, and it's probably the same in CCS. Thank you very much. Joonsang, do you want to go next?
Yeah, I can do that. Yeah, thanks. Yeah, there are many interesting topics and also useful for CCS to dig into more. And lately, at least in my nearby me, is the emphasis quite much on the integration of different discipline and different data set, and also different people. And for example, at NGI, we try to really make a close collaboration between geophysicists and geomechanics people, and also people in the lab, because individually we are doing quite well, but sometimes it's not clear to me what's the relationship between these different disciplines and different data set. And also I can see that quite often that when we understood very well about interactions between these different discipline and data set, and also how to transfer this knowledge to the other discipline, then actually you can save quite a lot of time and money, and also reduce uncertainties, because there are a lot of uncertainties in each individual data set. But you need to understand how this is really propagating between work in your whole chain of CCS. So something like integration and how that should be done, and that can be quite useful topic to study in many different directions.
Do you think that we have still a challenge with common language in all these different disciplines? Because that's something that has often been seen in other, like in energy, that quite often one discipline to the other might be talking about the same thing, but not exactly the same language.
Yeah, I think at least we are getting better. But still, I mean, new things are coming in and new people coming in. So then you have having different view. And although we have a high computational power these days, but still we are new things making us also quite challenging too. So I think we need to keep thinking of this integration and having the common language as well. Yeah, that's important to keep in mind.
I got a follow-up question for you from the audience. Is the challenge also on the various scales of the data sets? So is it also on the scales of the data sets or only on the disciplines transfer? I think it's related.
Scales of data set. What does it mean? Scales of data set?
I would think it's like upscaling, for example, from wells to seismic and things like that.
Oh yeah, of course, yes, upscaling, yes. We have a lot of issues because we have a lot of lab data, and we are very sure what we produced in the lab. But then, how to translate into log scale and larger scale? That's really challenging, and there you need to have really good communication between disciplines and understand what you produced, how this can be used in the different scale. Then you may have a different idea how your data has to be really solid, sound. Yeah.
Thank you, Joonsang. Elin, do you want to go next?
Yes, I can very much agree on Philip's comment on uncertainty, because I think that is a very important aspect, that you will never know for sure the subsurface. So you have to find a good way to address the uncertainty and include it into your risk evaluation. So that's one point. Then I see that the basis for a lot of the geomechanic analysis and for the pressure development is the in situ stress conditions, and I think there can be more work done on defining the stress conditions, and especially the heterogeneities, that the stress conditions are not equal all along in the reservoir. They vary in the reservoir, in the overburden, along the faults. There can be stress rotations, and including those things and just find simple ways of including it into the workflow, I think can be very useful.
I like that you say simple.
Just a reminder to all the attendees. Oh, sorry, go ahead.
No, I mean, yeah, we all want things to be simple, because I mean, there is not a lot of money in the CO2 storage project at the moment. So it's also about finding efficient way of utilizing the data that is available from how the subsurface have been used earlier. And I think there is more data than what we are using by now.
That's a very good point, the economics as well. Thank you. Anthony, you wanted to say something?
Yes, just a reminder to all the attendees, if you'd like to ask your question live, just raise your hand, and Laurie will move you up to ask your question to any of the presenters. I have one comment though, coming from the end of that last discussion, that yeah, I guess this might be even some discussion even for the third day in terms of regulatory requirements, but without a clear signal from the policymakers about a carbon tax, I guess there's not really the motivation for a lot of at least emitters to capture that CO2 and direct it towards storage. But there is an urgency if we want to meet our net zero goals within the timeframes that have been given from various parties.
Anybody wants to comment on that? No, but I fully agree with that. And I think that's a big part of what we want to explore on the third day of the workshop, because the regulation is a big part of what we can do in the future, and what kind of technology we can develop and use in an effective and economic way.
We have a question in the Q&A box for Joonsang, and the question is, can you elaborate on the need for dual component source and receivers to measure more accurately reservoir measurements that you had mentioned?
Yeah. Basically, I don't know if you remember my slide. If you don't choose the right the combination source and receiver direction and positions, you miss the target. Yeah, even in the same position, but if you happen to use only inline, not the inline and crossline source and receiver configuration, then you may not see it, the target. So yeah, so it's important to include the different possibility in your survey layout, but before that you need to know what's the expectation. So you should minimize what you need to bring on your vessel to go to the survey. Yeah.
Thank you.
Should we give the word to Peter?
Yeah, I assume that's still giving the students some advice, correct?
Yes.
Well, taking it from a second-year PhD student, maybe it's not directly on what to study, but rather your plan of approach. I live here on Svalbard, and the department is quite small, so every time I need to reach out, I need to contact people. So I think it's very important for people, not just here in CO2 business, but like everywhere, that you should be thinking outside of the box and try to really maximize everything you can get out of a certain data set, as also Ellen specified, but also not to be afraid of contacting others and asking for help. Prime example, like I know quite a bit about pressure, but I'm definitely not as good in pressure as Tom is. So for me then to just take some of the things that I've discovered about pressure and put it in the right context, and it's much better to ask an expert, like for example Tom, or if I want to do EM, well, get in touch with Joonsang, to really make the story happen. And I think that's my advice for the people that are still getting there.
No, and I think that's good for everyone. I mean, we need to reach out to our network and our experts.
Exactly.
Yeah, agreed. The internal and the external network are vital throughout your entire career, I would say.
How many companies are there to offer EM services? Acquisition, processing, interpretation. Are there enough for the tremendous growth in EM envisioned for CO2? That was a loaded question, but an excellent question. Everybody's smiling.
Yeah, I mean, as long as I know, there are at least 3, 4 that I know that who can do this, including acquisition. But there are many rather small companies who can offer processing and interpretation and inversion as well. So, but if EM is required, then I think it will be rather quick to be ready, because I mean we had a quite high activity in EM at least in Europe, Norway. So if some demanding is coming up, then it shouldn't be take too long time to be ready to go. Yeah, that's my, at least that's my expectation.
Thanks, Joonsang. I'll just add a quick comment at the end there, if I can. I think resistivity mapping for monitoring is fairly important, because the resistivity measurement is much more sensitive to the saturation of that injected CO2 than, say, the acoustic seismic methods. So ideally, the two together would be the best kind of monitoring. But if targeted correctly, the EM monitoring could be cheaper, and cost is, of course, a big concern.
And they had a follow-up comment that said basically, 3 companies are not very much for the global need of CCUS monitoring. Right? So I guess further thoughts on that?
Yeah, but actually I have to be a bit more precise than when I mentioned 3 to 4, that means offshore. But if you go to onshore, then you have many possibility in onshore. There are many companies who can offer you this type of a service. But the offshore is quite limited. That's not because of CO2, but I guess that's what happened in oil and gas industry lately, economics. So if things changing, then yeah, it's not difficult to make things happening. Of course, you need to put some effort, but it's possible.
I think we might be getting close to 3 offshore seismic operating companies as well.
Can I add something here? Of course, this all depends on the frequency with which we wish to do any measurements, right? And that again depends on the value of information, to use those terms. And I think that's another area where much more work, and especially also a lot of operational experience is needed. So which techniques deliver the best value for money, for example? Which techniques are most useful, and how often do we need to run a survey or to take measurements? That's all, as far as I know, it's up in the air. There's I think it's the Equistore project in Canada who has collected experience in this field and who have been able to scale down their initially rather extensive monitoring program over the years, and have gained insight in which of the subsystems, if you like, which technologies are most provide the most useful data. So that's the type of results and insights we need. And some of that will come from operational projects, but also some of that could come from R&D activities where we compare technologies that tell us something about the response of the subsurface to CO2 injection on sort of an equal basis, where again we take into account all of the uncertainties and try to estimate which one of them is better suited than the rest, for example. I think there's still a lot of work. And of course, the first couple of projects should make sure that we collect as much data and information and insight as possible, so that later projects can be made fit for purpose, or can be made as lean as possible, perhaps. And that then will decide whether we need 3 or 4 such operators, or 20 or 30. Thanks.
Yeah, those are all very good questions and very good points. I do believe there's a proposal in with the Norwegian Research Council and a SINTEF to at least synthetically model and try and work out the value of the information of doing EM monitoring, for example, on fairly realistic reservoir models. And yeah, of course, working out what's the optimal acquisition parameters, how often it needs to be done in time to ensure certain, well, monitoring of certain leak cases and so on. So yeah, it's not been done for real yet, not offshore as far as I know, but at least there's an attempt to answer some of those questions there.
Perhaps this is quite a good also a link between the day 1 and also to day 3, as Bill Library actually said as well. I mean, with normal monitoring schemes, you're looking for revenues, right? With these monitoring schemes, you're looking for methods that actually don't, let's say, don't bring too much costs. And that's something that will be interesting to see, you know, what is the, as you say, what's the necessary means of monitoring where you actually need the minimum, make sure that we have no risks, and also make sure that it stays in place.
Yeah.
Yeah, very good points. I can imagine that, yeah, that it's not a revenue generating exercise, but under an assumed regulatory framework, there would be penalties if it's not done. So it would be cost avoidance, I suppose, as determining the value.
Yes, and it's also a matter of, supporting operators as well as regulators. The regulator needs to understand the possibilities and limitations in order to set meaningful and useful requirements. I think a lot of governments, and I'm thinking of member states in Europe, a lot of governments are new or will be new to CCS. And I think a lot of them will have no idea. I think, like many of us, will have no idea what sort of frequency or technologies to use best. Well, there's a lot of work to do.
So coming back to the question for students, I guess there's a lot of work for people who would like to get involved in this kind of industry.
We have another question. Are there any industry consortia who are working on better understanding the various parameters and reservoir complexities associated with the whole CCUS project scheme?
Perhaps I can mention something. So it was presented on the first day by Bill Averill, and that's the CSEM, the SCG Advanced Modeling Corporation, that is doing, CSEM is doing a CCUS project that includes a life of field type of experiment in which, well, modeling experiment that is inspired on the life of field seismic project that was done or is pretty much just finished, where 8 years of production of oil and gas was modeled using geomechanics, gravity, seismic, everything. And now it's starting to be used, the same idea to monitor in a synthetic way the evolution of a field through injecting seismic and looking into microseismic, geomechanics, seismic effects, etc. And the project is also doing, or is planning to do, a digital twin. So they are still in the process of selecting a specific field to do the digital twin and try to model and forecast the changes. So I think this is an example of industry projects where you can see both operators and service companies working together to try to understand and provide some information to the development of the science. Does anybody know about any other one that you want to highlight?
Well, I'm sure the people from the NGI and UNIS CO2 have quite a history too in developing the technology, at least. Would they like to comment, perhaps?
Well, yeah, I can say that we do work with integrating a lot of the different parameters that we use to characterize both the reservoir, and maybe to an even larger extent at NGI we have worked with the seal and the containment in the last couple of years. But yeah, we definitely see that there is a lot of parameters that you need that are dependent on each other. So there's many aspects to kind of integrate.
Also, you have tremendous data of CO2, but it's not as I said, it's unconventional, it's tight, it's not the ideal reservoir which you are searching for. I mean, so, but the material which are on testing is unique. And of course, students are welcome to work, but they have to move very far north. Not everyone like to do that. So, but I think there is enough material to several PhDs and masters up there, if that's a point. So, and all data are open. There is no. I think that's a different from all the kind of studies the companies. They sometimes keep the data for themselves. These are open for everyone, as long as we are, or Kim, next generation, are informed.
And I think we've had many successful collaboration between UNIS, University of Oslo, and also NGI, and we have quite a lot of data that are like results in the laboratory from samples from Svalbard, but I also think there is, even if it's an unconventional reservoir, I think there is many fundamental aspects that can be studied, and yeah, and especially I think what we are all afraid of in the unconventional setting is that something is going to fail, like that you develop some fractures that can lead to leakage, and you have a lot of fractures that we can study to understand better these processes. So there's
but the nice thing is that leakage here is no problem. Maybe a fox and maybe a polar bear is passing by. So we are not any problem in that circumstances. So this is possible to monitor, and that in fact was one of the research council eager to support this study, was just to monitor leakage. They want leakage to see how they can monitor it. So that was one of the ambition for the research council.
But have you been able to do that so far?
We are not allowed to have carbon dioxide up here. So.
No, so, and now nothing else either.
That was ambition.
Yeah.
If I can turn around the question, ask me in different ways, in a different way, what would you see sort of like organization like ACG do differently, or do in addition to try to bring more focus to this topic? Anyone? Anyone you'd like to from your maybe for example for the students as well, right? For the PhD students, anything there? Because I remember when I was a student at NTNU, then we had all the data from Gullfaks, for example, in 1985, you know, and all those years, at least from seismic, was available to us, and we could do the processing, could study the data. And I'm assuming that's the same available now for this topic, right? But if the organization like ACG can support or can also move to facilitate something there in this regard, that would also be quite good to know.
Yeah, when you talk about, I mean, yeah, UNIS has a lot of data, but there has also been this data share project that SINTEF has led in collaboration with at least Equinor, are active sharing Smeheia data set, and they have shared Sleipner data set that there was just, it's not long ago, there was a kind of a benchmark study on the last seismic or last model from Sleipner. So those are available, as far as I know, freely available for everyone that are all researchers that are interested in testing out their modeling tools on those data.
There is Total is probably all of that data. It's a lot of data from Frigg field, And I think that they was depleted by 50 bar, I think, when production was stopped, if I don't remember wrongly. And that could be
something
really
like
nice.
that.
Yeah, I think that could be very nice for a student to really see if how fast the depletion, and I don't think anyone has done it. And now it's done on this bad accident in UK. What was it called? This,
Elgin?
yeah, no, the disaster with the platform that took fire. I think Marathon. I don't remember. Anyway, they did a depletion and reservoir study of how fast it come back.
Yeah, I guess there should be enough data
I think pressure
around.
is a very important issue. It's extremely important, I think, to really understand.
Hey, Shiv, I see that your hand is up.
Yeah, the question I had is, I'm not familiar with the state funding in Europe, but are there any state-funded CCS project anywhere in Europe? We have been trying to do that through USGS, and there is never any money available. But is there anything in Europe that's being done, a state-funded CCS project, like Norway or something like that?
Well, the CCS projects currently being developed in the Netherlands are fully state-funded. They're not operational yet, but once they are operational in about 3, perhaps 4 years' time, then they will be fully state-funded. Whether that means that we, as an R&D community, will have easy access, I'm not sure. Actually, I quite doubt that, because these projects will be storing on a commercial basis CO2 from a number of emitters. So they'll probably be very reluctant to let anyone near the system, because that just increases risk, right?
Yeah, it's probably fair to say. So, Adriana, please go ahead.
No, I was going to suggest you or Elin to comment on that as well from Norway.
Yeah, Elin, maybe you would like to comment, because at least Sleipner and Snøhvit are the ones which are basically, you inject back the CO2, which is from the production, but the Longship project is the one which is the forward going one, and that's the one which is state funded at the moment.
Yeah, that was what I was gonna say as well. That Longship project is, I'm not quite sure what is the deal. I mean, it's state funded, but there is also involvement from Equinor, Total, and Shell for the injection part, and how things are divided economically. I don't know.
But we'll find, actually, we have 2 presentations on the next day on this topic. Yes.
If I may add something, this is not direct state funding, but earlier this year, Tina Bru mentioned that the tax on CO2 emissions has been raised on the NCS from 200 NOK to 700, around 700 to 800 per ton. So that's actually to be used for as an incentive to lower tax CO2 emissions. So it's not direct, but it's a way of contributing.
Well, in the absence of state funding directly, the regulators, like what you mentioned, Adriana, have some sort of a penalty for not injecting that's what you need. The government has to support one way or the other, directly or indirectly.
It's very interesting, because we're also looking for, yes, the government will be supporting through that, but also the industry, the contractor industry has had the hit in the last years, right? Then there's that much that they can also take the hit, if further on. So that's also forward still thinking of what sort of methods we actually need to make sure that we actually get the minimum viable product view information from that, and then make sure that we actually receive that. And maybe if that's governments funded, or if that's there are other ways, that's interesting to see how it turns out.
I guess there is also EU funding that is being
Exactly.
put into CCS at the moment, and for the 2 capture sites in Norway, part of the Longship, one is state funded, but the one Klemetsrud in Oslo is, as far as I know, they are put on hold for state funding, and they need to apply to EU for partly funding, and then the state will go in with the support as well.
I think we should do some lobbying. You know, this is a very good forum. You know, the technical people could do some lobbying to the regulators and explain why it is so important to have funding, state funding, or indirect funding by regulations. So that would get the oil companies, operators, and so on, the incentive to do it.
I agree. It's quite obvious, isn't it? In Europe, at least, we see that CCS projects are developing in those countries that have state funding. So this is Norway, UK, Netherlands. They all have regulations in place on top of ETS somehow to make things feasible, to create the business case. And other countries that do not have, that only have ETS, if you like, the projects there can't get their business case closed. It's very obvious.
It's also important, I guess, to in this regard also to say that we have an infrastructure, oil and gas infrastructure, that also needs to be, you know, it will age with time, right? So this is another use for the same infrastructure. So it's sort of the good from both sides. We're also utilizing the existing infrastructure.
Looks like we have a comment that there are some projects in Germany currently ongoing.
Yeah, we had also had presentations on Croatia and Hungary in the last day as well. So it's true. Yeah. And I see also that many of these projects are phased. You know, they're coming with phase. For example, you know, Longship as well is there's a certain amount of CO2 being planned to be injected in the first phase, and then there's an increased amount if we also bring in the emissions from outside from all the emitters that we planned around Oslo or around Norway.
So there are projects of common interest, both in Germany and Poland, which I think both are interesting, because Germany has long been quite opposed to CCS, but now they do have an EU-funded project in their country, and more or less the same, I think, is true for Poland. So in both countries, we now see activities commencing to develop, perhaps not storage projects, but transport projects that aim to collect the CO2 from emitters to a location near shore, to a location in a port from where it can be transported further. So those are activities that help grow some confidence that things will grow in Europe outside of the North Sea area.
Yes, true. That we had, I think one of the maps we had on the first day showed quite a lot of potential emitters of the CO2 around Europe. So
Yes.
that's these places. Yeah, true.
I guess one of the views, of course, Europe has a better position in many ways to go to net zero and to do more CCS, etc. But we can also see an advantage there that a lot of, because of the tax system, because of the incentives from the government, and in the case of Norway, because of the system that also refund some of the money that is spent in research for the NCS, we can perhaps in this part of the world help developing technology that can be later used in other parts of the world. So we can also see this from a global setting as, okay, Europe has an easier path, is more developed, their use of energy, everything. So it has an easier path, but it's also a way of contributing to the rest of the world where the path is longer.
Agreed. It goes from through, as you say, through the whole chain of operation, from capturing, to transportation, and then also storage, and how to make it cost efficient on all the different parts.
So we need to make sure that we have some successful CCS projects in Europe, in those countries that has the possibility to develop them.
And share the experience.
I mean, we cannot ask some of the countries that are still struggling to get energy to everyone and to improve the quality of life. We cannot demand from them to have the same targets as we have in this part of the world, but we can help setting the path forward.
So open sharing of data and knowledge is then quite important.
And maybe
I agree. That's the only way.
To Emin's point about what else can a society like SEG do, and maybe that's part of the contribution, helping transferring information and open data.
True, it's a global type of organization, so that may be a good niche for this type of organization to get these links working.
Well, SEG can certainly do the lobbying to the regulators, to the government, senators, and so on, to the administration, to create an environment where they understand the importance of this.
Well, I suppose if there's any further comments or questions, please speak up. If not, it's I guess time to close our session. And once again, I warmly thank our speakers who've enlightened us greatly today on the specifics of the reservoir and storage problems, and to all the attendees as well for participating. And thanks to Laurie and the SEG for helping facilitate all of this, and finally, of course, our sponsors who've contributed greatly as well. Would anybody else like to make any closing remarks?
No, join us on the third part. I mean, we are.
Yes, don't forget that.
Yeah.
Thank you.
There you go.
Thank you for hosting.
Thank you.
Okay, thank you so much. Bye-bye.